This is a continuation of free response question number 3 of we having our two discs attached to each other, and going to B, we had one mass hanging off the smaller one, mass 1, and we had a mass 2 hanging off the larger radius on here, and we had it at equilibrium. Now the problem, moving on to B, is we're going to basically cut or remove the mass that's on this outside one, and it's going to be released, and we want to determine how fast will this spin going this direction, how fast will it spin once that one mass is removed? Well, there's a couple of things I know that can help me on this problem. First, again, I like the side view. It's a little easier for me to see what it is. We're removing this one. I have this. It is going to spin this direction. And it's going to spin at the same rate that this mass falls. So what we're saying is the string that is pulling or rolling is going to have my angular acceleration is going to be at the same rate that the mass 1 is also falling, which is really basically gravity, right? So we have two things that are going to help us solve this problem. The rotation, which was what we're looking for, the angular velocity, and the velocity of the object, the mass actually falling. So I rewrote it again, just a little bit clearer. And they also gave us a little extra information that we're going to need. The moment of inertia of the two cylinders spinning together, their inertia, what causes them to keep moving, is 45 kilograms per meter squared. So again, I know I want to find this acceleration, what it's spinning acceleration, and it's going to happen at the same rate that acceleration that this object falls. It is also happening counterclockwise. It's positive because my thumb is up. So I have two things happening, and this is going to help solve the problem. It's going to find out this is key. We have both linear rotation velocity, and also we have a linear and rotational. So if I use that to solve this, I'm going to worry about the rotation one first. So I have torque is equal to the inertia versus the angular acceleration. I know torque is going to be affected by how much force, or the tension of the string in this case, times how far the radius. How far is it out? Again, torque is how far something is out from its center point, causing it to spin. So I can substitute that in, and I'm going to find out, I solve for the angular acceleration, which is what I'm looking for, but I'm stuck with two unknowns. But fortunately, we've had this kind of situation before. I can look at the linear situation. I have free body diagram, those never went away, the force of the string, the tension, versus how much mass 1 and gravity are pulling it down. So if I do sum my forces in the y direction, I've got that mass, and I made acceleration going down as my positive. So I have that minus the tension is also equal to, I have movement, so I'm going to have mass times acceleration. Simplifying it, this is what I'm solving for, but I also know this type of acceleration is really, again, what we're looking for over here. So I have my angular acceleration times the radius, substitute that in, and I continue down. So now I have this force here that I can substitute back in to over here. And now it's just an algebra nightmare, really, to solve the rest of the problem. So I substituted that in, and I get all of this. And here's really the biggest problem. is I have this angular acceleration in two spots, so I just have to grind through my algebra. I brought this to the other side. I took the radius times the things on the inside, so I get a radius squared there. I'm going to bring this over to this side now. My angulars, get them on the same side. So we went from negative to positive on that side. Now I'm going to pull the angular acceleration out. So I have this. And then I'm going to bring this and divide it back into this side. So after all of that algebra, I am finally to this point right here where I can actually put in my values. And I do that, and I get that angular acceleration of 1.96 radians per second.